Swayam Prabha. Digital India. Educated India.
Today we will be covering on rotor dynamics, what is the state of the art. We will continue with the previous lecture in which we were describing the history of the rotor dynamics. We already saw the early history of the rotor dynamics, in which people solved the problem of the critical speed predictions and unbalanced behavior predictions after the critical speed. Also, we saw some of the instability which arises in the rotor due to the asymmetry in the shaft or asymmetry in the rotor itself. And now we will continue with this similar instability in the rotor system. So, and I have given this particular lecture name in the state of the art in the rotor dynamics. So, other instability have since been discovered. Prominent among these are those due to cross coupling stiffness in bearing and seals and steam hold, which can also occur in gas turbines. These phenomena, in which friction that ordinarily damped vibration causes self excitation vibration, attract the attention of many researchers. In the middle of 20th century, Horry in 1959 succeeded in explaining various fundamental characteristics of oil whip by investigating the stability of shaft motion and considering pressure forces due to oil films. The mechanism of vibrations due to the steam hold in turbines was explained by Thomas in 1958, and that in compressors was explained by Alford in 1965. The vibration of hollow rotor containing fluid is a relatively new phenomena of flow induced vibration. Instability due to liquids partially filling interior cavity of rotors was demonstrated by Coleman in 1962, and in 1967 Erich reported that fluid trapped in engine shaft introduced a synchronous vibration and also changed the shape of resonance curves. Kuipers in 1964 and Wolf in 1968 independently succeeded in explaining the appearance of an unstable speed range in a post critical region of a rotor system containing inviscid fluid. In 1980s, the rotor dynamics effects of seals in fluid handling machines received a great deal of attention. Rotor destabilization due to seals were predicted and demonstrated in an operational compressor by Jenny in 1980. As rotors became lighter and rotational speeds higher, the occurrence of nonlinear resonance such as subharmonics of half x, 1/3 x, etc. became a serious problem. Yamamoto in 1955 and 1957 studied various kinds of nonlinear resonances after he reported on subharmonic resonance due to ball bearings in 1955. He also investigated combinational resonances. Tondal in 1965 studied nonlinear resonances due to oil films in general bearings. Erich in 1966 reported subharmonic resonances observed in an aircraft gas turbine due to strong nonlinearity produced by the radial clearance of squeeze film dampers. These squeeze film dampers are identical to the general bearings. Only thing is that in this squeeze film damper, the stiffness property which generally general bearing gives to the rotor is not there, only the damping it produces to the rotor. Then Ehrich in 1988 and 1992 reported the occurrence of various type of subharmonic resonances up to very high order and chaotic vibrations in practical engines. This is a typical full spectrum plot showing the harmonics. Even can able to see the frequencies are there not only in the positive side, also the negative side, and we have seen earlier the concept of the forward fold and backward fold. So, you can able to see that some frequency components which are negative side belong to the backward fold and positive side to the forward fold. The non-stationary phenomena during passage through critical speeds have been studied since Lewis 1932 reported his investigation on the Jeffcott rotor. Non-stationary phenomena that occur are one in a process with a constant acceleration and another with a variable acceleration, in which we have the limited driving torque. At the theoretical analysis of such transitional problems is a far more difficult than the stationary oscillations. Many of the researchers have adopted numerical integrations. In this particular, when we are considering the transient rotor analysis, you must have observed to avoid the critical speed, that is to avoid the critical speeds, generally the rotors are given very high acceleration, so that they can cross the critical speed very quickly and go to the supercritical regions. And during the acceleration, the problem may come if the driving motor drive is sufficiently is having power, then there will not be any problem in that whatever the acceleration we want to give. But if drive is having less power, then the required acceleration will not be achieved, and you will be having problem that the variable acceleration may take place. Natanjan in 1952 studied shaft vibration at critical speed. Grobo in 1953 and 55 investigated in general form the shaft vibrations resulting from varying rotational speeds. The development of asymptotic method, that is analytical method, by Metropolsky in 1965 considerably boosted the research on this subject. There is an extremely comprehensive literature on the role of fluid film bearing in rotor dynamics. Development up to 1957 were largely due to Newkirk, who explained them in a very detailed and graphical way. Then beginning in the early 1960s, most attentions focused on hydrodynamic bearings. This was largely stimulated by Lund and Sternich and the Lund's work in 1962 and 64. Gunter's work in 1966 related to rotor dynamic stability problems combined with Roux and Brooker's 1972 and Lund's 1974 methods for calculating damped critical speed stimulated a great deal of interest in rotor bearing stability problems. Lund in 1987 gave a overview of fluid film bearing. In the mid of 1970s, the rotor dynamic instability experiences with various high pressure compressors and high pressure fuel turbopumps of the space shuttle main engine focused a great deal of attention on the influence of fluid structure interaction forces, particularly forces due to liquid and gas seals, impellers and turbine. Soumya in 1989 and Tiwari in 2004 compiled extensive numerical and experimental results and literature of dynamic parameter of fluid film bearings respectively. Shaft shields have similar effect as fluid film bearings. They influence the critical speeds, can provide damping, or on the other hand cause instability. Some of the first investigations were carried out in 1965 by Lomakin. Since then, shaft seals have acquired a significant role in their effect on rotor dynamics, as the extensive literature show in Child's book in 1993 and a review paper by Tiwari in 2005. Instability from fluid film bearings and shaft seals arise from the fact that during radial displacement of a rotor, a restoring force is produced which has a component at right angle to the displacement. Such a mechanism is possible for a rotor with blades as a result of variable leakage around the blade tips. The phenomena of instability was described in detail by Newkirk in 1924, whose interest was in turbomachinery. At first, it was thought that the cause was internal friction due to shrink fits of the shaft, and the theory was developed to explain this also, together with experimental verification by Newkirk in 2004 and Newkirk in 1924 and in 1925. Till now we have seen various literature review related to rotor dynamics phenomena and how people have attempted those phenomena. And now let us try to summarize whatever we have studied in a tabular form. So, this is a summary of various rotor dynamics phenomena and their details. Like whirling, it was that is related with unbalance was first. This particular term was used by Rankine in 1869, and this was theoretical work which described the general motion of the rotor system. Self-centering of rotor, this concept was introduced by D. Level in 1883. This I am again repeating this. Self-centering of rotor was described by D. Level in 1883. This is a theoretical experimental work which gives the unbalanced response of rotor. Then the synchronous whirling was introduced by Foppel in 1895. That is also a unbalanced response with theoretical response. Critical speed concept was introduced by Dunkerley in 1895. This is a resonance phenomena. Second critical speed was observed by Kerr in 1916 in his experimental setup. A stable supercritical response was first analyzed by Jepcott, and based on his analysis, a particular rotor model was available to the rotor dynamics community, and he described the damped unbalanced response of the rotor after the critical speed also. Then secondary resonance due to gravity was explained by Scodola in 1924. Instability due to shaft asymmetry by Prandtl in 1918. Gyroscopic effect, that is rotor wobbling, it was described in the Scodola's book in 1924. Threshold speed, spin speed for instability, that is due to the internal damping, was described by Newkirk, Campbell and others. Threshold speed for instability for dissymmetry of bearing stiffness was described by Smith in 1933. Oil whip was observed by Newkirk and Taylor in 1925. Self-excited vibration due to contact was first reported by Baker. Oil whirl in hydrodynamic bearing was in more detail described by Horry in 1959. Steam fold was reported in steam turbine by Thomas in 1958. Flow induced vibration in hollow rotor containing fluid was described by Coleman and others, both theoretical and experimental works. Instability due to seals was reported by Jenny in 1980. Subharmonics and combination resonances due to nonlinearity in the ball bearing was reported by Yamamoto in 1955 and 57. Nonlinear resonance to oil film in journal bearings was described in great detail by Tondal in 1965. Subharmonic resonances due to squeeze field damper was reported by Erich in 1966. Non-stationary response due to constant and variable acceleration of rotor speed was described by Lewis in 1932. Shaft vibrations at critical speed, that is varying spin speed, was dealt with Natanjan in 1952. Again I am repeating, shaft vibration at critical speed due to varying spin speed was described by Natanjan in 1952. Then the shaft general motion, that is for varying spin speed, was described by Grobo in 1953 and 55. This was theoretical work. The damped critical speed of hydrodynamic bearing was explained by Roux and Booker and Lund's work in 1974. They use FEM and T, that is finite element method and transfer matrix method respectively. Now, we will begin with another phase of the presentation, in which will be, this is the outline of the presentation, in which development of the rotor dynamics analysis tools I will be describing. So, dynamic balancing of rotors, that is how the development took place. Software for rotor dynamics analysis, some of the software I will try to review. And then I will come to the condition monitoring of the rotating machinery, a brief review on that, and then conclusion and the recent trend. So, now we will review the development of analysis methods for continuous as well as multi-degree of freedom systems, and that allowed practicing engineers to apply these methods to real turbo machinery. The lecture also summarizes work on vibration based condition monitoring and recent trends in the area of rotor dynamics. So, let us see the development of rotor dynamics analysis tools. The rotor dynamics, a remarkable amount can be explained by a dynamics of a single mass Jeffcott rotor model. We have seen that there was confusion in the history of the rotor dynamics, and Jeffcott rotor, Jeffcott he clarified those confusions, and because of this particular rotor model is very popular and very helpful in analyzing the most of this simple rotor behavior. So, this model introduced in 1895 by Foppel was named after Jeffcott, because in 1919 he explained the science of rotor dynamics in a graphical and illuminating way. Gradually, the Jeffcott rotor model in its many variations came closer to the practical needs of rotor dynamists of the day, but not close enough. Vibrations of rotors with continuously distributed mass were studied. In the rotors, actually we can able to model that as a discrete masses or continuously distributed property. In continuously distributed property, both the mass and the stiffness of the shaft varies along the length of the shaft, but in discrete system the lump masses are conducted by a massless springs. So, these are two different models. As we will go into the subject more detail, we will able to appreciate these terminology. So, The simplest continuous rotor model corresponding to the angular beam was first studied in the book by Stodela in 1924. This is the typical turbine which we can able to analyze by the present whatever the analysis tools are available with us. The critical speed of shafts with distributed mass were also examined by Gramin in 1920 and 1929. In 1950 and 1960s, Bishop and their co-workers like Parkinson, Gladwell, they and along with the Dimmenberg, Tondel, they reported a series of papers and books on unbalanced response and the balancing of continuous rotors. Elshman and Eubanks in 1969 derived more general equations of motion concerning the effects of rotary inertia, shear deformation and gyroscopic moment, and investigated these effects. The rotary inertia, shear deformation, gyroscopic effect, these are generally called higher order effects in rotor dynamics, and we will see that as we will go into the deep into the subject how these phenomena or effects they affect the natural frequency and critical speed of the rotor system. Many practical rotors, especially those being designed for aircraft gas turbines, were not suitable for a Jeffcott model. For one thing, the distinction between disk and shaft is blurred in a typical aircraft gas turbine. In the practical design of rotating machinery, it is necessary to know accurately the natural frequencies, mode shapes and force responses to unbalance in a complex shape rotor system. The first systematic procedure for analyzing realistic rotor dynamics model, however, gave as much importance to internal forces and moments as they did to the displacements. The method of Holger in 1921 for torsional vibration was of this type. Engineers could apply this method using only a slide rule. A more general modeling techniques was needed. This was supplied by Prohl in the late 1930s and published in 1945 for critical speed evaluation of turbine shaft. It is similar to the method published about the same time by Michael Stead in 1944 for the natural frequencies of aircraft wings, but was developed independently. Of course, Prohl's method was designed for a rotating structure rather than a stationary one. Together, Prohl's and Michael Stead work led to a broader method now called transfer matrix method or TMM. This method is particularly suitable for useful for multi-rotor bearing systems and has developed rapidly since 1960s by contribution of many researchers including Lund, Goodwin, Rao, etc. The TMM or transfer matrix method for rotors remains viable. Indeed, it seems still to be the method of choice for most industrial rotor dynamic analysis. Another representative technique used for this purpose is the finite element method. Although most of the concepts used in finite element analysis were described by Courant in 1943, the real development of the finite element method as engineering tool occurred in a decade later with the introduction of digital computers and the formulation of structural analysis in matrix format by various researchers and then used in various technological fields. The name finite element method first appeared in the title of paper by Clough in 1960. The first application of the finite element method to the rotor was made by Roux and Booker in 1972. Then Nelson and McVock 1976 generalized a generalize it by considering rotary inertia, gyroscopic moment and axial force. It was soon recognized that the large number of nodes necessary to provide accurate stress distribution created dynamic system too large for economical calculation in three-dimensional solid model of such rotors. Now, we will see how people in industry they were balancing the rotor and how the very sophisticated method of balancing of such rotors based on vibration took place in the history. The most important and fundamental procedure to reduce unfavorable vibration is to eliminate geometric imbalance in the rotor. The balancing procedure for the rigid rotor was established relatively early. A practical balancing machine based on this technique was invented in 1907. The arrival of high speed rotating machinery made it necessary to develop a balancing technique for flexible rotor. Two representative theories were proposed. One was the modal balancing method proposed in 1950 by Federer, Bishop and Gladwell. The other is the influence coefficient method proposed in late 1930s by Rathbone and later by Thurley in 1932, developed mainly in the United States along with the progress of computers and instruments for vibration measurements. This is the basic concept of a rotor unbalance in a long rotor. You can able to see the first is the perfectly balanced rotor. The geometrical center and center of gravity, they are in the line with the center of axis of the rotation of the shaft, first figure. Second figure, there is a static unbalance, that means there is a radial offset of the rotor from its center of axis of rotation. So, because of this there is unbalanced force. Second one is the long rotor got tilted by some amount, and because of this there is a couple which acts, and the magnitude of this couple is actually can be given as this is the angle of the tilt of the rotor, omega is the spin speed, IP is the polar mass moment of inertia, and ID second one is the diametral mass moment of inertia. And the fourth case is the combination of the moment and the force due to not only the tilting of the rotor, also due to the radial shift of the rotor. So, this will produce both force and moment, and you can able to see that the case B require a single plane to balance, but case C and D would require two plane to balance. This is a rotor with long rotor, but this is a flexible rotor. So, you can able to see in general the eccentricity will be varying radially also along with the angle, and in this particular figure the center of gravity exaggerated just to demonstrate that it can vary like this, but generally it will be the eccentricity will be of the order of microns, and you can able to appreciate that the first one is when the shaft is near the first critical speed. So, we have half sine wave. So, we can able to balance this by single plane at mid span, but when we are operating in the second mode, so is full sine wave, and we require two planes to balance, so that we can apply force one in this direction and one in this direction, so that these displacement of the rotor can be minimized. and the same we can able to see if we have more number of modes, so that many number of planes will be required to balance the rotor. Now, we will see some of the tools, because the methods people were developing to analyze the rotors. Simultaneously, development of the computers were taking place. So, people were developing indigenous softwares for analyzing the rotor, and these softwares, indigenous softwares, then gradually became some of the software as commercial ones. So, let us see them in the subsequent slides. So, the World War II can be considered as the demarcation between the early stage of rotor dynamics and what might be called as modern rotor dynamics. This was the consequence of two factors. First, there was a growing awareness of the contribution of rotor dynamists from non-English speaking countries like Demenberg in Russia, Tondal in Czechoslovakia, Kramer in Germany, Yamamoto in Japan, among many others. Clearly, after World War II, rotor dynamic analysis had become an international endeavor, a fact that was recognized by the founding of the rotor dynamics community of the International Federation of Theory and Machines and Mechanisms, that is called IFTOM. Beginning in 1982, international conferences have been organized by this committee in Rome, Tokyo, Lyon, Chicago, Darmstadt, Sydney and Vienna. Second, there was a revolution in solution capability, a transition from somewhat simplified method to almost actual geometry. In 1960s, there was a collection of various numerical methods applied to structural dynamics and of digital computers capacity that fostered the development of series of general purpose computer codes in this particular field. The initial application of these codes to the rotor dynamics was based on the transfer matrix method, but in the 1970s another underlying algorithm, the FEM, became available for the solution of prevailing beam based models. Now, in the beginning in the 20th century, the rotor dynamics are combining FEM and solid modeling techniques to generate simulations that accommodate the coupled behavior of flexible disc, flexible shaft and flexible support structures into a single massive multidimensional model. Rieger in 1974 was the first to review the rotor dynamics softwares on the market. At that time, he concluded that the development of rotor dynamics programs has lacked the support afforded to other area of structural dynamics. Crandall in 1992 gave an overview of the rotor dynamics computer codes like ANSYS and other softwares were available in the market. The classical Jeffcott rotor with 4 degrees of freedom was used to illustrate free, forced and self-excited vibration problems for rotor dynamic systems. He also concluded that with regard to quality and quantity of software, the specialized area of rotor dynamics still lag behind the broader field of non-rotating structural dynamics. He gave two main reasons for this, that the rotor dynamics market is small and the technical problems are more difficult. Now, I will review a very important aspect of such rotating machinery, that is condition monitoring, because now whatever the theory of development of analysis, these rotors or rotating machineries are well developed and various rotating machineries are operating in the industry, but during operation frequent failures are occurring, and because of that these condition monitoring techniques are getting more popular so that both the money and the manpower can be saved. So, in 1960, cracks were found in rotors of some steam turbines. To prevent serious accidents and to develop a vibration diagnostics system detecting cracks, research on vibrations of crankshaft began. In 1970s, Gash, in 1976, Harry and others investigated vibration, giving consideration to the nonlinearity in stiffness due to open closed mechanisms. They showed that an unstable region appeared or disappeared at the critical speed depending upon the direction of the unbalance. And other area in which lot of development took place is the assessment of turbomachinery condition monitoring and failure prognosis technique. In this particular condition monitoring, there are different level of condition monitoring is possible. First is the detection of the faults. Second is the diagnosis of this. That means people try to find out what is the severity of the fault. Then next level is after finding the severity, whether we can able to quantify what is the life of the machine with that fault. That means whether we can able to find out what is the remaining life of the machine, so that either we can able to operate the machine for few months or few hours, and we can plan the maintenance accordingly, or there is a urgency, or there is a some kind of I am repeating this. There are different level of condition monitoring which we can able to do. First is the detection of the fault, in which we detect the fault, and second stage is localizing that fault. So, in that we try to find out where is the fault in the machinery. Third stage is in which we try to quantify the fault. That means that particular fault is having how much severity, and the fourth stage is in which we can able to find out how much time more we can able to operate the machine with that particular fault. So, that is the useful remaining life of the machine we can able to predict, so that we can plan the maintenance accordingly. So, high performance turbo machinery are now extremely important element of worldwide industry. The electric power, petrochemical, mining, marine and aircraft industries are prime example for which turbo machinery is crucial for business success. Failure and resulting downtime can be very costly to the industry involved. According to Elsman, over the past several years, instrumentation and monitoring capability have increased dramatically, but the techniques for fault diagnosis have been evolved slowly. So, this is a typical modern, that is condition monitoring system, that is on site condition monitoring system, in which you can able to see there is power plant here, and there is a various kind of information regarding this can be sent to an expert system, which will be storing data, maybe the present data and history data of the plant, and that can be sent through server through internet to a remote web browser, where the expert can see the condition of the machine through analysis. These power plants can be at different places, and at central place some expert can view this and analyze this particular data. So, the tools are therefore still more advanced than the techniques, and there are three technical area that must be addressed for effective fault diagnosis using vibrations, that is condition and fault mechanism, modification of signal transmission path and signal analysis. Edward in 1998 provided a broad review of the state of the art in fault diagnosis techniques with particular regard to the rotating machinery. A detailed review of the subject of fault diagnosis in rotating machinery was then presented. Special treatment was given to the area of mass unbalance, bowed shaft, cracked shaft, these being amongst the most common rotating or rotor dynamics faults. Vibration response measurement yield a great deal of information concerning any fault within a rotating machinery, and many of these methods utilize this technique are reviewed in this particular paper. Some other reviews provided broad overview of development and progress in condition monitoring, diagnostics and failure prognosis techniques applicable to high performance turbo machinery. Cracks in shaft have long been identified as factor limiting the safe and reliable operation of turbo machinery. They can sometimes result in catastrophic failure of equipment, rotor bursts, and more often in is costly process upsets, repairs, and premature scrapping and replacement of equipment. In the past 3 decades, much research and many resources have gone into developing various online and offline diagnostic techniques to effectively detect cracks before they cause serious damage. Subnovices in 2004 reviewed literature on cracked shaft detection and diagnosis published after 1990. One of the earliest documented application of acoustic emission technique to rotating machinery monitoring was in the late 1960s. Since then, there has been an explosion in the research and application based studies covering bearing pumps, gearbox, engine, rotating structures. Some other researchers like Ma and Rao in 2006 presented a comprehensive and critical review of application of acoustic emission technology to condition monitoring and diagnosis of rotating machinery. So, now we have already reviewed various analysis tool and condition monitoring tool. Now, let us see the recent trend in this particular topic of rotor dynamics, so that the new researchers can see what is the openings in the research in the rotor dynamics field. So, the latest topic in rotor dynamics is the study of magnetic bearing, is a mechatronics product and which supports a rotor without contacting it, and it gives a active damping effect. This study was reviewed considerable attention since the work reported in 1975. We are now a long way from the approach of Jeffcott and Proyle, a journey that deserves its own history sometimes. So, this is one bearing. Actually, this is a squeeze film damper, which is a passive damper. You can able to see this is the inside is some kind of rolling element bearing. The shaft is attached to the inner raceway of the bearing. These are rolling elements, and then here is the outer ring, and this outer ring, and there is another casing here. In between this, there is a fluid cavity. So, as such, this outer ring is not rotating, only the inner ring is rotating, and during motion of this ring in the up and horizontal and vertical direction, the fluid which is there between this will get squeezed, and that will provide damping. So, this is because the outer ring is not rotating. So, hydrodynamic action will not take place, only the squeezing action will take place, and this is generally used to dampen out the resonance in the rotors to provide more damping in the system. Now, let us see some active fluid filled dampers, in which you can able to see this is a rotor, this is a bearing, and here active device is there, in which this is similar to the squeeze filled damper, but only thing is that whatever the fluid is there, the property of that is getting changed because of these electrodes. Those fluids are special kind of fluids, either they are rheological fluid in the form of magneto-rheological fluid or electro-rheological fluid, and if we change magnetic flux or current through these electrodes, the property of those fluid changes, like stiffness and damping changes, and it gives different damping and stiffness to the support system, and this can be changed actively. This is a magnetic bearing, active magnetic bearing. This is a rotor which is floating on the air. The sensor measures its vibration and it gives to the controller. Controller gives required current to the amplifier, and this amplifier gives required current to this actuator, so that the required current can be given to the actuator, and this will produce magnetic field to pull the rotor up or down depending upon its motion. So, this is actually active magnetic bearing. So, this is one of the research area which is active, and we know the advantage of these bearings, that because the rotor is floating on the air, so there is no lubrication required, friction is less, there is no mechanical contact, and generally only the high speed whose limit is the strength of the material, there is no problem in the as such the speed constrained by this particular bearing friction. Only the rotor strength should be enough to have that much speed. With this magnetic bearing, not only we can suppress the resonance, also we can able to have online balancing, and because we can able to change the stiffness and damping property online, and these are the some other advantage we can have, like we can able to eliminate the instability in the system also. So, in the last two lectures we have seen the introduction to the rotor dynamics. We have seen the history of the rotor dynamics, even the state of the art in the rotor dynamics. To brief these lectures, especially what is the recent trend, that is very important. As I have already mentioned, that one of the area where we should focus, that is on the bearings, because bearings are still, they are not, those models are not capable of predicting the actual behavior in the bearings which are there in the industry, and most of the case the bearing gives instability. Their properties are hard to find using available theoretical models, or if theoretical models are there, the difficulty is getting the proper property which these models requires. There is a difficulty in that. So, the more research is required toward the bearings. Also, the foundation of the such rotors are very important. They also play a role in the dynamics of the rotor. Apart from this, in the bearing we have seen some kind of active bearings have come up. They are still required research, so that they can be more reliable. Apart from this, we have various phenomena which are nonlinear phenomena in the rotor dynamics, that still require more investigation, because several people have studied mainly the linear analysis in the rotor system. With this, we conclude this particular lecture. In the subsequent lecture, we will see some very basic analytical models and analysis of the rotor dynamics. Now, in the long rotor case, I will show another case in which, let us say, this is the original axis of the bearing, and the shaft axis is inclined by some angle. Let us say this angle is phi x. So, the rotor is basically inclined like this. I have exaggerated the inclination just to show this particular inclination. In this, the center of gravity is there on the bearing axis. So, both geometrical and the center of gravity at the same place. So, when this particular rotor is rotating with some RPM, there will not be any centrifugal force, because center of rotation and center of gravity are at the same location, but there will be a moment because of this inclination, and that particular moment will be IP minus ID omega square and the angle of the rotor axis with respect to the bearing axis. And for this particular case, because now moment is acting onto the rotor, we require two planes to balance this particular rotor. Maybe you can able to choose one this end, one this end, and we can able to either put some mass at particular radius, another mass at some other particular radius to balance this particular moment. And once we have this particular moment value, and so these can be obtained using moment balance in this particular plane. And another case is when we have, let us say this is a bearing axis and rotor axis is not only inclined, but is having some offset, radial offset. So, in this particular case, you can able to see that the rotor will be having these are the bearing. Rotor will be having a force which will be m e omega square, and there will be moment which will be same as the previous one because of this tilt of the rotor. In this particular case, we have both moment and the force, and when we try to balance this particular rotor at these two locations, we will be having two different mass at different radial positions. So, they can be used to balance both forces and moment. So, for both the cases, the previous case and this case, we require only two planes to balance the rotor, and this particular kind of balancing is called dynamic balancing, and because rotor is rigid, so that is why we require only two planes to balance. In subsequent lecture, we will try to derive these relations when we will cover the dynamics balancing of the rotor.